Okay, so we can start on lecture 14. We're going to talk more about nonlinear difference equations. So last time we just started talking about what they would look like, fixed points, how to talk about the stability properties of fixed points, which depended on the derivative of f of x, right? So if I had a difference equation that looked like this, I had to find the derivative of f of x and understand whether or not it was its absolute value was less than 1, right? To say whether or not the equilibrium, or that would be at an equilibrium, to say whether or not the equilibrium was stable or unstable. So let's dive in a little bit more to understand how nonlinear difference equations work. So say I have the following just nonlinear equation, right? So g of x is 0, this guy here. And so we're looking for equilibria, right? So this would be like the right-hand side of the difference equation. Let's say we're looking for x star, which is a solution. So we said solving algebraic expressions is much easier than solving differential equations, and so that's why we kind of like finding equilibria in nonlinear systems in particular, but it can still be kind of hard. And so let's talk about ways that we can do this in approximation or numerically. So let's say that we have a solution here, but we want to define some difference equation, some iteration that gets us to the equilibrium if we don't know it analytically at first. So I'm going to approximate it using a linearization. So let's say we have 0 is g star here, sorry, g of x star. So that's the true equilibrium. And I'm going to add and subtract some x of k. And then I'm going to try and define an iteration for x of k that gets me close to this. Well, this is like a Taylor, I can think of this like a Taylor expansion, right? Where I have it around some number. So around, for example, my xk. And x of k, if it gets close to x star, is going to be somewhat small, right? And so this would be like g of xk plus the derivative of g of xk, x star minus xk, and so on. So this is just a first order Taylor expansion or a linearization, right? Where I group these two terms. This would be like my perturbation on this guy here. So if this is like A, this is H, this is A. If you're used to that notation, this is H. So if I solve for x star, where I just take the extreme right-hand side equals the extreme left-hand side, so 0, I get that x star is approximately equal to xk minus gxk over g prime xk. So this is what's called the Newton's method iteration, or this suggests a Newton's method iteration. If I say the right-hand side would be the value at xk, and then I iterate this method for a bunch of k's, making the left-hand side just xk plus 1, then what I'm hoping is that this xk plus 1 term approaches x star. So this is Newton's method for finding roots. Finds roots of, in general, nonlinear, but of course you can put a linear function in here. Of nonlinear functions. Awesome. So let's look at an example. So let's consider this cubic, right? So this cubic polynomial is not the easiest to factor, right? In general, solving cubics is like not that easy, which is why I said, you're not going to do that on your tests or whatever when you were in class. But if I forget this -1 for a second and just factor these first two terms, that's pretty easy, right? So what we can do is use this factorization, forget about this for a second, and say that the roots of this polynomial have to be somewhat close to the roots of this polynomial. This is my approximation. And I can use the roots of this polynomial as initial conditions for a Newton's method iteration to find the 3 roots of this nonlinear equation here, of this cubic that's hard to solve in general. So let's look at, so the roots of this, by the way, are at 0, -1, and 1, right? Let's consider the root that's kind of near 1. So let's define x naught is equal to 1. And I'm going to use Newton's method to try and find a couple of terms of this difference equation that should approach, hopefully, the equilibrium where gx star is equal to 0 as we take steps going forward. So x1, so Newton's method says this should be x0 minus gx0 over g prime x0. First of all, oops, going to move up a little, here we go. So g of x is x cubed minus x minus 1. So g prime is 3x squared minus 1. So if x naught is 1, when I plug 1 into here, I have 1 minus 1, so I have a minus 1 in the numerator. And then I plug in minus 1 here, so I have 3 minus 1, so a 2 in the denominator. So I have 3 halves for my x1 term. Okay, let's do x2. So this is x1 minus g of x1 over g prime x1. So it's going to be 3 halves minus, let's see, gx1. So I'm going to plug that into here. I have 3 halves cubed, so 27 over 8 minus 3 halves minus 1 over 3 times 9 over 4, so 27 over 4 minus 1. So we need to do a little algebra. Let's see, so 27 minus 12 minus 8 all over 8 divided by 27 minus 4 over 4. So 3 halves minus, let's see, 27 minus 20, so 7/8 over 23 over 4. 3 halves minus 7 over 8 times 4 over 23, otherwise known as 3 halves minus 7 over, let's see, 2 times 23 is 46. So, like, it's a number, right? So this is 2 times 23, 3 times 23, minus 7 all over 46. Good gracious. What's this? 69 minus 7, so 62 over 46. Whatever this number is. I guess we can divide by 2. So 31 over 23. So some number that's like a little bit bigger than 1. Great. So if we do this algorithm a bunch of times, we hope that it approaches the equilibrium that's close to 1. We're going to look at that in MATLAB. But before we look at that in MATLAB, let's think for a second about what this means geometrically. All right. So this curve here, oops, is g of x, right? Okay. And I'm starting at x is 1. So I'm going to give an initial condition here. Okay? So this is x1, or sorry, x naught, g of x naught is this point. So what does, oops, another parentheses. what does Newton's method mean? Newton's method says xk plus 1 minus, or is equal to xk minus gxk over g prime at xk. Okay, so g of xk over g prime at xk. So if I think of the slope of a line, which is the derivative of a function at a point, right? The slope of the tangent. So slope is like rise over run. What I'm looking at over here, this is rise, right? This is the change in the y values, say, the functional values. So if I have slope is rise over run, this is like I've divided both sides by slope and multiplied both sides by run, right? This is like run is equal to rise over slope, which is exactly what this is. This is the rise over the slope. What it means is I'm going to walk along the slope of the tangent line. How far? Until I go the distance of the functional value. So if I draw, okay, be gracious, let's see if I can draw a tangent. Looks kind of decent. Here's a tangent. If I want to get to x1, I take the functional value, and then I'm going to add on the rise of the function walking along the slope. So I've walked along the slope to here, and I'm going to hop back up to the function here to get x1. This point is x1. I mean, this is also the same value, x1, and gx1, because I drew it on the function. Now, if I draw another tangent, now I have to walk along this tangent. I guess I should have mentioned first, right here, I'm going to draw an x. That's where it looks like the function crosses the x-axis, right? So now I'm going to walk along the tangent again. In this case, I'm going to walk down. And actually, you'll notice in the algebraic calculation that we did previously, when I went from x0 to x1, I had to go negatively. So I moved to the right along the function. And now these numbers were both positive, so I subtracted. I had to move left, right? So I have to walk up the tangent. Now I'm here, I've kind of overshot, and now I have to walk to the left to zero in on this root of the function. So that's the geometric interpretation here. But let's talk about how we do it numerically, because in reality, we want to run this algorithm numerically. So this is the MATLAB code. I've put it on your sheet here, but it's a little bit hard to see. So what I'm going to do is I'm going to change the screen here and share my MATLAB screen if I can do that. Let's see. Here we go. So hopefully that worked. And I'm going to walk you through what this code does. So I'm going to give first the number of iteration points, which is 6. And I'm going to initialize a vector that's 7 long because I want to put in the 0, the initial condition. Then we define my initial condition at 1. I have this here just for plotting for later, but I don't think we use that anywhere. Now I'm going to run my for loop. For steps 2 until n plus 1, I'm going to do the Newton's iteration. So I'm going to do x at k, like our k plus 1 term, is the previous term x at k minus 1, and then this thing here. We'll go into what it is in a second. So this is my function at k minus 1 term divided by my derivative at k minus 1 term. So what are those? If I go down here, my function is x cubed minus x minus 1, right? I put in x, I get out a y, and my derivative I put manually, 3x squared minus 1. And that's it. So if I run this, I'm going to plot the points from 0 to n. I shift them because, of course, the initial index is 1. I'll plot the points of this iteration x. And I'm also going to take the functional value for the last x, which hopefully is close to 0, right? So I run this. I guess I'm not sharing the screen with the plot. New share. So here's the plot that came out. So it starts at 1, pops up to 3/2, and then starts to go down to this, whatever this root value is here. It looks like something close to 1.32. And when I look at the functional value here, back to MATLAB, it's basically machine 0. So we've done a really good job of approximating the root of this function. Okay. Just briefly, so we know we had other roots, right? So we said we were starting off near 1, but say we started off near -1, right? We thought there was a root that was going to be near -1. Let's see what happens then. Okay. Maybe we'll look at this in a second. Hold on a second. I think we're going to go through this in a minute. So yeah, I thought we would do it a little bit out of order. Let's stop sharing for a minute. We'll go back to the camera, which is out of focus. Okay, let's see. So I put in my new plot. So I put in your notes the plot that we just plotted. And of course, Canvas will have the MATLAB file to generate that, but we looked at that before. Okay, so let's get back to the method and talk about the method a little bit. So we have the method here, and what I want to ask you to do is to show that if I plug in an equilibrium, and as long as this denominator is non-zero, then we have an asymptotically stable fixed point of the difference equation. The difference equation is this, if I see the right-hand side, is f of x. So let's remember what an asymptotically stable equilibrium point means, right? So stable is that if you start close, you stay close. Asymptotically stable is that if you start close, you stay close and you approach it as k goes to infinity. So it's not saying it will always converge, but it's saying that if I start close enough, it will converge. The algorithm will converge to the equilibrium. So let's see. Let's plug in to this iteration what the equilibrium would look like. Remember, testing asymptotic stability said we want to look at the absolute value of the right-hand side's derivative, f prime, right? So f at x star, let me sure, can you see that? Yeah. So f at x star is x star minus g at x star over g prime at x star, right? And then if I take the derivative of this guy with respect to x and then plug in x star again, which I'll just do it all in one step. So f prime at x star, the derivative of x is 1 minus, we can think of this like the quotient rule. So the bottom times the derivative of the top, I get 2 g primes at x star. So 2 of these guys, so it's squared minus the top gx star times the derivative of the bottom, so the second derivative of g at x star, and then over the bottom squared, g prime at x star, again squared. So this is the same term, right? So this is really 1 minus 1 plus g x star, g double prime x star over g prime x star squared. Cool. All right. So what we wanted to show was that if g at x star is 0, which it should be if x star is an equilibrium. If x star is a fixed point. That's what we've been calling it, a fixed point. G at x star is 0, so it's an equilibrium for the difference equation, which means I have 1 minus 1 over here, that's 0, and this term is 0. And the denominator is non-zero, so we're good, which means that f prime at x star is equal to 0, which is certainly less than 1. So by last lecture, you see that? Whoops, sorry. I was writing off screen for a while. Here you go. Okay. So this was the derivative that we did. We said this is 0. So if we had x star as a fixed point, then g of x star is 0, which means f prime at x star up here. These two terms sum to 0. This is 0. This is non-zero. That's going to be less than 1, of course. And then by the last lecture, we saw if f prime at the equilibrium is less than 1, then the equilibrium itself is asymptotically stable. X star is asymptotically stable. Sound good? Well, okay, sorry, no one's talking. Okay, the other question is, does the method always converge? And the answer is no, it doesn't always converge, because if I start too far away, the iteration is going to go someplace else. We haven't seen that, but we can maybe imagine that. The reason being, we'll think you have 3 roots for this, right? So if I start close to one root, which is asymptotically stable, the iteration will go there. If I start close to another one, the iteration will go there. But it's not going to go to both at the same time. So of course, they both can't be asymptotically stable, if that makes sense. Okay, so let's consider this exercise. Let's look at a slightly modified polynomial, another cubic, that I want to solve. So it has 3 roots, but it's kind of hard to factor. So let's just look at factoring the first 2 terms like we did before to get initial guesses for these 3 roots, and then modify the code that I just showed you together to find those 3 roots. And then make sure that we do enough iterations so that we get the g of x case sufficiently close to the root. So less than 10 to the 10, doesn't have to be machine 0. And then we'll plot the function, and we'll plot the roots, and we'll see if they look like they're correct. So the first kind of bit of work here is, how do we factor x cubed minus 4x? So I can take out the x, and I get x squared minus 4. So x is x minus 2, x plus 2. If I set that equal to 0, the roots should be near x is 0 and plus and minus 2. So those will be our initial guesses for the Newton's method iteration that we'll do for root finding. So let's go to MATLAB and work on this. Okay, so I'm going to open up a new window.